Okay, here we are. I've got some announcements first. For those of you who are I wanted everybody to hear them. Basically, we had our fourth test will be, we have 2 more weeks of classes. A week from Thursday will be your fourth test. It'll be on the gas chapter, and the last chapter we're doing on orbital things. So essentially gas laws, energy will be covered in the next semester. So in Gen Chem 2. Okay, so basically, yes. I believe it's chapter 10 for the gas laws. You can check that, chapter 10, and we're continuing with chapter 8 now with that. So chapter 9 will be covered in general chemistry 2. And if I'm scheduled to teach just labs this next semester because basically the decision was made to have the tenured faculty continue to teach with their things. I only have one section. This section is the only section I have. So basically, the other professor is scheduled to teach it, but I'll see many of you in the labs anyway, and I hope we'll have a good time because general chemistry 2 labs, believe it or not, are more fun, particularly if we can get out of the virtual ones. Gen Chem 1 labs are more procedures. Gen Chem 2, you start getting to good stuff, like seeing colors change and such like that. So basically, and organic chemistry is even funner. So any other questions? Okay, anybody distant, any other questions there? Those of you who are virtual.
Dr. Douglas, what was the curve on the test 3?
Same as the other ones, about 15.
Okay.
And basically, as I said to the people here, it was because some people opened questions, they answered the wrong question, or in the multiple choice, they might have answered the wrong question or missed a nuance there, sort of, but I can't give partial credit on the multiple choice. So basically, that's how it works. So it's fair. It was consistent with the previous grades too. Basically what I saw was most people improved their grade from the first and the second, I mean. So, okay, any other questions? Okay, let's get going now. I'm going to continue now with chapter 8 of our book, but it's the next chapter 10 in Chang. And again, I don't like the PowerPoints in the other book. So basically we'll make the best what I can with this one. But if you do have any questions, the PowerPoints for our book are there. I encourage you to use them. And again, I encourage you all to continue to read chapter 8, work the problems within the chapter, email me or message me if you have any questions on them while you're doing it, and then work problems for each section at the back of the chapter, okay? And many of you did that between the second and third test, and it really showed on your test score. So all I can say is congratulations to you in that situation. So let's start now. I'm setting up the PowerPoint. I got to find the right place to go with this. Okay, we're going to have a little bit of an overlook here, here with this. I'm going to now share the screen with you. Okay, can everybody see the screen there? Can you folks see the screen distance? Are we okay? Can you see it? Hello, could someone distant say something?
Yes, I can see it.
Okay, wonderful. Thank you very much. Okay, so let's give things, this kind of refreshes where we did the last one. The main things that, yes. Oh, sorry. They were just. Got it? Okay. So what I'm going to do now is go over each of these and basically help you understand how these work. These are the main forms that you're going to see. And as we go through today's and Wednesday's lecture, essentially it'll help you understand how these all fit in with what you've been learning about B, S, B, P, and D orbitals, okay? So there are a bunch of topics that is important, and the experiment 13 worksheet, you can finish it off based on what we did this week, so I encourage you to do that and use it to help you, as well as the modeling one. Now, for those of you in group 2 for the labs, no, group 1 for the labs, you're going to do that modeling lab this week, and the labs that you did last week are due this week. So basically that's how that works. Yes? Well, if there isn't one on there, don't worry about it. Okay. Or you can write in a paragraph yourself what you learned, okay. But I just want you to fill it out, okay? Okay, so basically the key thing is, again, you have, you have linear here, linear, okay, tetrahedral, okay, and you really need to learn these. Trigonal planar, okay, and remember trigonal brings up triangle, and then trigonal bipyramidal, and then octahedral. So you have octahedral here. I'm not going to try and fit in all the other one there, but those are the ones I want you to learn. The T-formed and all the other ones, T-shaped and everything else, they're just variations of it, so don't worry about that. The only people that really need to worry about that are chem majors. So basically, that will help you understand how it works. Now, there's a bunch of different varieties of tetrahedral, but I'd like all of you to look at these things here. What are the similarities between the 3 pictures on the screen? What are the similarities for each of these? Anybody, volunteers here. I'm not going to pick on people. I just want volunteers. What are the similarities between the 3 pictures? Yeah, okay, good. They all form what else? A pyramid. And what else do they have? They all have 4 lobes, but the red ones are different from the green. Why are the red ones different from the green? Yeah, you have lone pairs in them, and they're not constrained by a nucleus, okay? They essentially can wander, and so it's a little bigger. Okay, so basically what happens is because the atom repels things more effectively, the angles change. And no, I do not want you to memorize those angles. I just want you to understand why they're different. Why are they different based on the model we covered last week? Why are they different based on the model we talked about last week, the valence shell electron pair repulsion model? Why are they different? Because the electron pairs repel the other atoms differently, okay? So the angles are going to be different. It's like there's a stronger repulsion for certain ones than others, okay? And basically that's the key thing regarding each of them. Now you have lone pair versus lone pair repulsion on the first one, lone pair versus bonding pair repulsion on the second, and then bonding pair versus bonding pair repulsion on the last one for the bond angles associated with each, okay? So basically you have lone pair in the bonds themselves versus bonding pair related to it, and then bonding pair versus bonding pair. And basically that fits very well with why it does this. Now, the VFCPR thing, if you have the number of bottoms thing, you have trigonal planar again with an electron pair at the top. That's trigonal planar again, but it is called bent. And bent is one I want you to know also, okay? Because bent also fits water, the water molecule, even though the water molecule is a little different. So basically, if you have the water molecule in there, tetrahedral with NH3. That's trigonal pyramidal. And then you go to the next one there where you have two of them, tetrahedral, and that is bent. So bent is important. It's just a different kind of bent, okay? There's a bent with one electron pair and there's another bent with the other, okay? The bent with one electron pair tends to be more planar than the other one would be, just because of the nature of how it works. Now, if you have AB5 there, trigonal bipyramidal, and again, that's the one I want you to know, distorted tetrahedron. Don't worry about that name, but it's useful to see why is it distorted? Yes, very good. It's going to repel it differently than the others will. Okay, it's just distorted, but it's just extraneous information you don't need to know. So on the coming test, you'll be asked to give me the geometry things, but I'm not going to play tricky stuff with you and ask you to show me a T-shaped, okay, or that one, okay, and then AB3E2 there, trigonal bipyramidal, and then T-shaped. No, you will not be asked to reproduce that, okay? Even though chem majors and those who are motivated to continue to study it may want to do it just for fun. I've had students that like to do this because it was fun doing the Lewis dot structures. Believe it or not, when I was in college, I enjoyed it, okay? Because I grew up playing Tinker Toys. So in a way, it was just putting pieces together and I could picture it better that way. Okay, and then AB2E3 here, trigonal bipyramidal again, and that is linear. Why is it linear? What keeps it in a linear form? Yeah. Correct, correct. And the atoms will want to stay as far apart as possible too. So there's two factors there. The lone pairs kind of circle it, and the other one goes up and down. So that's why it will be linear. But it's different from this. Why is it different from, sorry, why is it different from this one? Why is that linear? Why is that linear? How's that different? CO2. Well, here you got a double bond here and a double bond there, an electron pair sticking out. So that keeps it in line also for other reasons. And we'll get to that in a few minutes. Okay, and then you got AB6 octahedral, looks like that. You got square pyramidal. And then the next one, octahedral square planar. Now, I could ask you the same question. Why is that one square planar instead of octahedral? What's the nature there that's similar between that and the octahedral one? Well, again, you got the electron pair at the top and then the four atoms around holding it in place, okay? So they both work together, same, just as the ones with three. Okay, so then you add the rest. Yes.
Will you go back for 2 seconds?
Sure. You have a question on this specifically?
Can you explain why it's square planar again?
Well, what is on the top and what is on the bottom? Are they atoms there or are they electron pairs?
The electron pairs.
The electron pairs. And the four green things around, which are fluorines, they'll want to stay as far apart from one another as possible, right?
Yeah.
So what happens if you put a green thing up there? Will it be as far apart from the other ones as possible? No. Okay, it'll be closer to the other one over here. So basically they'll tend to repel each other. That's the repulsion again happening. Okay, now predicting molecular geometry. Well, you draw first the structure for the molecule. You count the number of lone pairs of the central atom and the number of atoms bonded to it. You use VSEPR to predict the geometry, okay? So if you have a bunch of different ones, SO2 and SF4, you can see the differences between both of these. The SO2 looks like this. So what will this geometry be? The SO2, what will that geometry be? Bent, correct. Yes, very good. Okay, because you got this electron pair then, and then the resonance forms going between each oxygen. Yes. Sure. But you just say bent. It's easier for you to picture it for yourself. The two kinds of bents. That's just a slight accommodation to what I'm saying. This fits. Yes.
How do you know that it's not linear? Because if I were to draw that, I feel like I would just draw it straight across.
Because there's this electron pair at the top that prevents it.
Okay, so
Any extra, an atom or electron pair will prevent it. Okay? That's why a common mistake that people made on the last test was putting the hydrogen on the sulfur instead of an oxygen, because the hydrogen will not want to go there. It'll want to attach to the oxygens at the end for HSO3. That's just one example of that. With if you have HSO3, which I had on the last test, and basically you put the oxygens in 3 places around the sulfur like this, and then people put the hydrogen there. No, it's not going to happen. It'll want to go over here, just because of the fact that these will want to have resonance forms and form a nice structure.
and so the CO2, that's linear because there's no extra electron pairs.
Yeah, because there's an electron, there's a bond called a pi bond on the next to it, which hold it in place. And I'll show you that, I believe, either today or Wednesday. There are 2 kinds of bonds: single bonds, which are single bonds, and then pi bonds, which are double. And that gets into the hybrid orbitals that I'll explain in the next topic. Okay, so SO3 like that is bent, and then SO4, AB thing is distorted tetrahedron. But you can say with that one, it is the it is the different one that fits the distorted tetrahedron. Now, the dipole moments and polar molecules, when you have situations where you have an electron pair area, like, for example, electron pair around these fluorines, okay, this is polar. And we've already defined polar in the previous chapter, but it has what is called a dipole moment that is directly related to this vector. And the vector is where the math comes in. That's the nature of the dipole moment, and that is calculated by using various experimental methods. So basically, dipole moments are very, very important in understanding molecular theory. And this is the plus is at the plus end, and then the minus is at that end. So if you have, say, for example, carbon with the hydrogens all around it, and remember, this is a 3-dimensional structure, which has a higher electronegativity, carbon or hydrogen? Just see if you remember which one. Carbon. So where's the arrow is going to be pointed? Towards the center. And because they're equal in magnitude, it cancels out. That's one reason it's nonpolar. But if you put a chlorine here, what's going to happen there? Where's the dipole going to go on that? To the chlorine. And that'll make it polar. The only way it's not going to be polar is if it's, the only way it will be polar with multiple ones is it's totally symmetrical. And I'll show you that later.
So Dr. Douglas, it's going to be the electron-rich region just has a higher electronegativity.
Well, yeah, a higher electron presence more, and it's usually going to be the one with higher electronegativity. Yes, and electron affinity also. Yes.
What's the definition of that?
Well, that's a mathematical term, and it's going to get into this now. The dipole moment is the Q, the charge, times R, the radius. And that may be a problem you have in the problem set, and it might be on the next test, but basically you'll be given that equation, or you can write it down on your card and just be, if you're given the charge and given the radius, then you can figure out what is the dipole moment of this, okay? Q is the charge, R is the radius between, and then the dipole there is 3.36 times 10 to the minus 30 cm, but again, that's what physical chemists have to deal with. You don't.
Dr. Douglas, so what's that symbol that's like kind of like an infinity?
That's a micro thing. That's a micro thing. That's representing the dipole moment. That's called the dipole moment, the mu.
So what do we need to know about it?
Nothing. Just be able to use the equation if it's given to you. I do encourage you to work some problems with open book to just practice the problems, just the math. But other than that, for this group, no, you don't have to. I want you to get the big picture of what this is. Okay.
So then
What
what is, I'm sorry.
Yeah. What is the more electron-rich region, the fluorine or the hydrogen?
The fluorine.
Yeah. Very
But
good.
what about the U is equal to Q times R? What's the U stand for?
That's the mu. It's a Greek letter. That's just the dipole moment. That's the specific number that they get experimentally. It's a term like a distance or like a force or something that would be measured experimentally. It's just the Q is the charge and then R is the distance between the charges. That's the dipole moment, and it's given as 1D for that. One dipole moment is 3.36 times 10 to the minus 30 cm. So, but that's the units. Behavior of polar molecules. When you have polar molecules, what do you look about? What happens with these? How are they orienting around those in those shapes? Correct. Okay. That's why water. That's why water is a liquid. Is because of the polarities between them. Okay. So and basically, if you have a water molecule that looks like this, another one there. This will be a positive region, this will be negative region, and so this will want to coordinate with another water molecule over here, like this, okay? So essentially, they will interact with each other. This is the positive side, this is the negative side, and that's why water has what's called, that's why water has a surface tension associated with it, or why when it freezes, it expands, because those bonds become important, called hydrogen bonding, and other things related to that. If you have a field, this is an electrical field, if you have electrical field turned off, they'll all orient around that. But if you turn it on, a magnetic field or electrical field there, they'll tend to be all in a line, so that you have a negative side and a positive side on the other side, and they'll all orient all in a line there if you want to do that.
Dr. Douglas, what was the value of one dipole again?
Well, if you ever need it, that's given to you. Right there, that's the value. The dipole moment is just the measured quantity of how polar that dipole is. Dipole means two poles, plus and minus. That's what dipole means. So the dipole moment is just the number that's calculated.
Is that unit?
Yes, I guess that's the unit, yes.
No, but is that unit centimeters, or what is the unit?
See, coulombs meters. Coulombs is charge, but if you haven't had physics yet, you won't know what coulombs are. Okay, but again, this is just putting in context that at this stage, all you're going to be asked to do is work the problems there and take the author's or my word for it that at this stage, this is kind of, you take it there. Okay, so if you turn on electrical field, it'll line up. Now, bond moments are a result of dipole moments. This will answer your question, Brandon. See that 1.46D? That's the number that happened with this thing. If you notice, the dipoles pointed all towards the nitrogen, which is more electronegative, and then one out, and so the dipole moment is 1.46. Now, what do you think the dipole moment would be, the overall dipole moment would be for the resultant if it was 0.00D? What would that be, a polar or nonpolar molecule? Nonpolar, yeah, very good, because they all cancel out. Okay. And so essentially you've got, this is vector algebra. And most of you did not have vector algebra. But I taught a college course called Advanced Algebra that included that in it regarding vectors, okay? Okay, now if you have this one with nitrogen and fluorine, notice the dipole's different there. Why is the dipole different there with fluorine instead of hydrogen? Correct. And even the top number will be lower because it'll drag this electron pair closer to it, closer to the nitrogen. So basically that dipole will be different. It's just an adding of the vectors together. That's how you get the dipole moment for that molecule. Okay, now which of the following molecules have a dipole moment? How would you answer that question? Yeah, so you draw the structures. So basically I'll just do it real quick. And I encourage you to try it for yourself. Okay, is that polar? Yep. How about this one? Nope, because this cancels that one. Okay, they cancel out. SO2, and I'm leaving the dots off. This is resonance forms again. Is that have a dipole moment? Yep. And then CF4. Yes or no? No. Okay, because they all cancel out. So now I'll delete my wonderful art and let you see it on the screen for yourself. There, the dipole is going in that direction. One net dipole there, polar. Then here, they cancel out. No net dipole moment. This one is polar, dipole moment, and then CF4, not polar. Okay, now BF3, does that have a dipole moment? Where's boron on the periodic table? Yeah, but where is it? What's this Lewis dot structure going to be? 3 around it, yeah. So basically it'll look like this. Oops, like that. Go with their art. Okay, so which direction do the dipoles go? They all go out and they all cancel each other. And again, if you were to line up these vectors to have a vector up like this, you can shift the vector and this one would shift up like that there, and this one would shift and go back there. So if you adding the vectors together, this is vector algebra again, the resulting is 0 there. That's why it thinks, because they essentially all cancel out. Because part of vector algebra is you can move the vectors in space wherever way you want to. Okay, and that's the structure it looks like. And notice it is flat. It is trigonal planar. It's flat because there's no electron pairs on the top or the bottom, and the fluorines will want to go stay out from each other. Does this have a dipole moment? Yes. Why? Well, you got the chlorines that are more electronegative than hydrogens, so one side will be different from the other, and so basically you get a certain thing that looks like that, and so yes, that will be polar also. And basically these dipole moments are experimentally determined. Microwave ovens essentially work by vibrating water inside the meat or whatever else, causing the water molecules to vibrate. That heats the stuff up there. Now, how does Lewis theory explain the bonds in hydrogen and fluorine gases? Well, you have the sharing of 2 electrons between the 2 atoms. And then you have bond enthalpy and bond length. Okay, the bond enthalpy has to do with the energy required to break it. And the bond length is going to be smaller with hydrogen just because hydrogen is very small in the first place. Okay, and basically the valence bond theory, bonds are formed by the sharing of electrons from overlapping atomic orbitals. In other words, if you have a hydrogen, it will be an s orbital like this, plus another hydrogen that looks like this with an s orbital like that. The melding of those two s orbitals will look like this. And essentially that was now bonded with an electron over here, an electron over there, going around both of them at the same time. This is called a sigma bond. Okay? And that is an overlapping atomic orbital. Okay? And if you were to put down the Lewis dot structure form for it, what happens to those two dots? Where do they move? Well, they form a bond here. And so basically you now have the electron pair in the middle here, and of course they go around both of them, and you got a big oval thing like that. Okay, now if you were to do on a diagram, and this was what physical chemists do, there's essentially a minimum here of the potential energy. This has to do with the hydrogen here, and essentially it's one big glob. And the distance, this is the r, this is the radius where the potential energy is lowest. And basically, if you were forcing the hydrogens to go closer to one another, potential energy would go way, way up. And if you gradually pulled those hydrogens apart, the potential energy would go up also, because they'll want to release like a spring and go back to each other until you finally pull them apart and they ionize. Okay, so basically the key thing is this potential energy has to do with how close it is, like pushing two north parts of a magnet together, or pulling it apart, like breaking a rubber band. Essentially, if you pull a rubber band and then let it go, it'll go back to its normal form. Well, bonds work the same way unless there's enough energy that causes it to break. Okay, so basically the potential energy is totally zero when the bond is effectively broken. The change in electron density as two hydrogens approach each other. You start with these two like that, and essentially you end up with this structure, and that is with what is called a sigma bond. And it happens with an S plus an S, you get a sigma bond. And it just happens to be the label that goes with it. Now, ammonia, okay, you have this here with 1s2, 2s with these. And how many hydrogens do you have? 3. Where the hydrogens, where the hydrogens will be like this, right? You have one dot there, and one dot there. So what's going to happen with those extra electrons around it? It'll essentially fill it up. So this will go there and go there, this will there and that there. So the resulting structure looks like this. This has 8 valence electrons around it. It is now bonded. This is these are the shared ones between these three there where they came in. And essentially you have an S coming up, this S orbital coming up to a p orbital looks like this, and then merging with it. Remember, this kind of p, there's one in there too, and essentially you get this combination where you have the S and the P, so this side gets bigger, this side gets smaller, and you got what is called an Sp3 hybrid between both of them, and that essentially is what is formed when you have these structures. And again, if you see it as a little ball of gum or rubber or something, gum, and you put it with a longer thing of gum, and you bring it close to another ball, you can cause them to stick together, and it'll be a big glot of gum, okay? Or you just have a longer bulb one, and you get a big one, and you can have an Sp hybrid there. So basically, this is also a sigma bond with this kind of structure. So you can have an S plus an S goes to form a sigma bond that looks like this with 2 of them next to each other. Okay, and you can have an sp hybrid where these extra electrons fill in there as well. And I'll get rid of my art and show you how it does it on the slide.
Dr. Douglas, what do you mean by an S? Like that's not sulfur, is it?
No, the S shell, remember? This 1s2, 2s2. This is the S here. What is the electron configuration of hydrogen?
1s1.
1s1, right, that's the S, okay? It looks like this with an S shell shape, correct?
So helium would be a sigma bond.
No, helium is just one atom because it's got 2 electrons around it already and it's just one atom. It doesn't bond really with anything because the other electrons already take it. But if you took 2 hydrogens, another 1s1 here with another one around it, this would merge together to get a bigger structure that looks like this. This is H2. And this has 1s there and 1s there merging together to form a bonded structure. And then you end up with that as well. Did that answer your question, Brandon?
So can any, like, if you have a like nitrogen and nitrogen, is that a
Well, we'll be getting to that because it has a sigma bond and also pi bonds, which are coming up, which I'll define next. But right now we're talking about sigma bonds, which are just single bonds between in S and orbital, S orbital, or S and a p orbital. Okay, so let's look at the slides here, how they do it. You put in 1 hydrogen, 1 electron there, 1 electron there, 1 electron there. If bonds form the overlap of 2 p orbitals on nitrogen with 1 s, what would the molecular geometry of NH3 be? And basically, you have the combination of all of them together. If these 3 2p predict 90 degrees there with that, if you use the 3 2p orbitals with that, but actually it's 107.3 because you have an electron pair at the top. So basically you have all these here with this, plus you also have that electron pair at the top, which is essentially right here. You have, these are the outside ones. This is the electron pair at the top, and these are the 3 bonds that look like this. Okay, so essentially you've got an S and then the P3 filled, and that's called an sp3 orbit. That's called the hybridization of each of these because they all become equal. They all become equal in magnitude or whatever and direction, except for the electron pair at the top of it, which is at the for the nitrogen that is not involved in bonding. Hybridization, the mixing of 2 or more atomic orbitals to form a new set of hybrid orbitals. Okay, this is what we're going to finish off today, and I kind of illustrated that in the previous slides. Mix 2 equivalent atomic orbitals, S and P. The hybrid orbitals will have different shapes from them. The number of hybrid orbitals is equal to the number of pure atomic orbitals used in the atomic hybridization process, and covalent bonds are formed by the overlap of them. And that's what I was referring to here, where you have an S, and then you have another S coming together, and the overlap of both of these are both hydrogens coming together, you'll get this, the structure that looks like this, hydrogen H2, that essentially will now look like this with that, and that's called a sigma bond, and that is a covalent bond where those electrons are shared between both of those atoms equally. The overlap with other hybrid orbitals here, and essentially that would be with a S plus a P that happens to be available on the next one, like on the nitrogen. These will kind of overlap there, and you get a big blob on one side and a small one on the other, and that is called an SP. And I'll show you there. You have the Sp3 hybrids there. The hybridization looks like that. Okay, That's where I was going with this. That's what the hybridization looks like. And which of the directions is a big N point? How many directions is a big N point? 4, good. And that's tetrahedral, okay? 4 points of that thing. And it's called hybridization. They're Sp3. The formation of covalent bonds in there. And essentially, these are S. Remember, you just have 1 electron around it. These are like this, these are like that, these are like this. And if you were to draw out the electron configuration of the valence shell for carbon, you would have, it is 2, for carbon, that it is helium, and then you have 2s2, 2p2. But then essentially what happens is that you now get, essentially, if it looks like this, with it going up like that and down like that, and then 3 p's like that, this one will shift and go back here. And so now these are equal. So you have 4 of those. That becomes Sp3 hybrid there, because now you have 4 places it can bond, and that's where the 4 hydrogens go. Okay, and now this part of the book, I could only address it a little bit with a lecture, but the main part of understanding this part of the chapter is by reading it. Okay, so read it today and work the problems in it, and then you'll get the bigger picture for how this is all supposed to work. Sp3 hybridization in ammonia. Well, what's different about it? What's different about it there? Yeah, the lone pair, correct. And you'll have the bond angle there, and it's a hybrid orbital there, look like that. The sp hybrid looks like this. And so basically with sp hybrids, essentially when you have 2 of them, if you have beryllium like this, it has one up like that, and then the p's are empty. You have another you have another one that's chlorine on the other side, but basically this will shift, the Be to form a bond will shift, and you'll get a structure that looks like this. These are now, but you have one like that and one like that, and so the result there is what is called an sp hybrid, and basically it ends up being like that because now these have come to be an sp related to it. And here, these are the extra holes that are available for other things to come in if you have anything to add to it. But basically the chlorine fills in, the chlorine, which of course has 7 around it, fills in like this, like that. And each one of those goes in with the chlorine and then the other chlorine next to it. This chlorine goes in there, just like they showed with that. And the formation of the sp2 hybrid looks like that with 3 of them. And basically you can get those also. So basically if you have the next one on there, that would be boron. Like boron, its electron configuration is this, up like that. And then you have one up there and then another one like that. This will shift and then go to there, and essentially you now have sp2 hybridization because this s orbital has moved up to this, and now they are all of equal energy. Okay, so you get sp2 hybridization, and it all looks like that with the boron in the center, and then 3 chlorines off of it. 3 fluorines like that there. And how do you predict the hybridization of the central atom? You draw the structure, count the number of lone pairs and the number of atoms, and then you can determine what the hybridization is for each. Okay, and then 5 like that, sp3d, and I'll get into more of that description with these ones later on Wednesday. But basically this is enough for today. Any questions? I will go to another set of slides on Wednesday also to give you another perspective on it. Chang is pretty good, but there's another one that's good too that hits it from a different direction. And I think the combination you'll appreciate better. Any questions? Okay, we're done for the day. I'll see you folks on Wednesday. Or if you're in my lab tomorrow, Tuesday. Yes.
What's the virtual lab that group 1 is doing this week?
It's the modeling one. It's number 8. It's like my experiment 13 I already gave you, but it's number 8. It's, yeah, you can print it out and watch Dr. Powell's video.
Okay.
Any other questions? Those of you who are distant. Okay. Have a good time, everybody.
So I was